All right. Well, moving right.
I'm the main event, huh?
Yes, you are. But let me introduce you first
Yes.
before I pass it. Oh, no, you can stand up here. This is Dr. Hal Levison, and he is one of the more famous astronomers, especially in the area of galactic dynamics. And he recently won the National Brower Award, which is one of the highest recognition of work. So let's give a round of applause for Hal. And his background is he attended Franklin and Marshall College out in Pennsylvania, where he helped to run the planetarium. So he has a long tradition of education and public talks. He went on and got his PhD at the University of Michigan, and he is the creator of some of the most widely used, most broadly recognized and appreciated software for modeling the dynamics of our early solar system. And Hal helped to found the Southwest Research Institute in Boulder. He was one of the original founding members, and that has grown to be over 100 staff and scientists now. And Hal is the principal investigator of NASA's Luci mission, and that's the topic of his presentation this evening.
Thank you. I'm going to put this sort of low. Well, maybe I can't. That worked. Yes. Watch the beard because it'll scrape. Can you all hear me? Yeah. All right. Well, that would have been true even without this, but so as you heard, I'm the principal investigator of the Luci mission. Think of me as the founder and CEO. Right, so this mission is my concept. I put together the team. We submitted proposals to NASA, one of, I think, 28, which we won. Okay, this is a mission to the Trojan asteroids, and I'll get into that in a minute. Before I start, I just want to point out that this is almost entirely a Colorado mission, right? The science and everything is done through SWRI in Boulder. The spacecraft was built in Lockheed Martin in South Denver. The launch vehicle was United Launch Alliance, which is in South Denver, right? The instruments and things came from other places, but it's almost entirely Colorado, right? I think Colorado, my wife will correct me if I'm wrong, in Colorado, aerospace is the third largest industry in the state. So lots going on. Southwest Research Institute, right, was home of the New Horizons mission to Pluto. It's the home of Luci. We have Cygnus running there, which is looking at the Earth and studying the growth of hurricanes. So there's a lot going on around here when it comes to this field. All right, so let me start by just talking about the role of small bodies and why we're interested in going to asteroids and comets. So in addition to the 8 planets, and yes, there are 8 planets, okay, in the solar system, there are these populations of small bodies scattered around. So here's the inner solar system, here's Venus, Earth, Mars, excuse me. Do I have all of them there? Yes. The asteroid belt, right, and then the 4 outer gas giants. And these small body populations are key to understanding how everything came to be. My interest, and I'm very weird for a PI for a mission, I'm a theorist. So before Luci, I just did large-scale simulations trying to understand how this structure came to be. Yeah, that was too fast. Let's go back. I have to worry about which things I'm hitting. These small bodies were formed and sculpted with the planets. But unlike the planets, which have changed a lot just because of internal processing since they formed, these things have remained relatively unchanged at the beginning of the solar system. So as a result, we sort of call them the fossils of planet formation. If you want to understand where the solar system came from, this is the place to go. Okay, matter of fact, Luci is named from the Luci fossil, right? To make that connection that these populations are going to tell us about our history. By the way, that was named from Lucy in the Sky with Diamonds, and if you notice, our patch is diamond shaped to make that connection. And I'll talk a little bit about that in a second, that history. So the planetary community has understood this for a long time, and as a result, we've sent a lot of spacecraft to study these small bodies. You can see all the ones sort of floating around. But if you noticed, here's the Kuiper belt outside the orbit of Neptune, right? Here's the asteroid belt. But there's these populations right here and here called the Trojans that have yet to be visited. Okay, so that's basically what we're planning to do. So what is Luci? It's a tour of these Trojan asteroids. These are objects that lead or follow Jupiter in its orbit around the sun. They always stay around 60 degrees ahead or behind the planet. The way to think about it is if you have a planet or an object exactly 60 degrees away from Jupiter, the gravitational attraction of Jupiter plus the sun and centrifugal force sort of all balance out. And if you stick something there, it stays there forever. Right, so these things are ancient primordial population. We launched, and I'll show you some beautiful pictures of the launch. It was really great. It was early morning, it was dark. It's one of those beautiful launches. I'm not going to show you a video, but if you have a minute, search for videos of this launch. Even the people down in Kennedy said it was one of the most beautiful launches they've ever seen. And I'll explain to you why when we get there with some of the pictures. We're going to rattle around the inner solar system for a while, have 2 rehearsals at 2 main belt asteroids, one that's coming up in November, and the other one is in 2025. And then we're going to have 5 encounters with Trojan systems between 2027 and 2033. It's a long mission. I'll be 75 when this is all over. And for a total of 8 Trojans, because one of the objects, which I must admit is my favorite, is a binary, and I'll talk about why it's my favorite at the end. But we also have discovered 2 satellites as we've been studying these things, preparing for the encounters, making a total of 8. So the scientific motivation of this, as I've already said, we've never seen one of these close up, so we have no idea what they're going to look like. And also, because of the proximity of these things to Jupiter, this is the only small body population that is not contributing to our meteorite collection on the Earth. So while we have comets, we have main belt asteroids, we do not have any Trojans. And so they really are a mystery. And one of the surprising things when we started studying these things from the ground is despite the fact that they occupy a relatively small region of space, they're very different from one another. And this is a mystery. And we know that by basically studying their colors from the ground. There's several ways of looking at this. The way I like to talk about it is they're what we call spectral types, right? Where an object that we call C-type is almost gray. Here's the reflectance. So the fact that it's flat means it's reflecting as much blue light as red light, and as a result, it looks gray, right? And then as you go down on this list, the P's and D's, they become redder and redder, meaning that they reflect more red light than they do blue light, right? And when you characterize these things, my thumb is just way too big. No, I need, yes, why don't we do that? My thumb is pressing both buttons.
I have little fingers.
Yes, I can tell. So when you characterize it, what we find is that the population is roughly half Ds, which are really red things, half Ps, which are sort of pink things, with a little bit of Cs, these gray things mixed in. And this is going to become an important part of our story, right? I should say right up front is we have no idea why these things are these colors. When we look at them spectroscopically, they're just flat. We don't see, at least in the visible and near infrared, we see no spectral features. So we have no idea what makes red red and what makes gray gray. And that's one of the things that Luci is designed to find out. And again, I'll talk about that a little bit more in a couple minutes. Next slide. So, but I think, remember, my history is trying to understand the history of the solar system and building dynamical models of how things moved around and how the planets grew. And I think what this is telling us is that these different colors represent objects that formed in different locations in the solar system and got mixed together during the evolution of the solar system. One of the, I'm going to use as an example something called the Nice model, mainly because I'm one of the authors of the Nice model, that hypothesized that the 4 giant planets actually formed in a much more compact configuration than we see today. So this is Jupiter and Saturn, Neptune and Uranus in this case, all formed close to the sun. So for example, astronomical unit is the AU, is the average distance between the Earth and the sun, right? Jupiter is currently at 5 AU, but Neptune is all the way out here at 30 AU, right? So we're starting off with something that's much more compact in this hypothesis. And then there was a disk of small bodies that stretched just outside the orbit of the outermost ice giant out to around 30 AU and it stopped. This population, you could hypothesize, has different colors because they have different chemistries on the surface because they're at different temperatures as they formed. So you can imagine now, and I just did this by hand, that the inner objects are gray and they become progressively redder as you get out in the outer part of the solar system. This hypothesis, next slide, you have to stay awake, is during this, this evolution, we believe that the orbits of the giant planets went unstable. Uranus and Neptune started crossing the orbit of Jupiter and Saturn, got scattered out into the disk. The disk just went kaplooey. Stuff in that disk rained all over the solar system. Matter of fact, the basins on the moon, the seas that we see, are probably the results of some of those impacts from this event. Okay, eventually the ice giants settled down to the current orbits, and you have this disk is basically gone, with a little remnant out beyond the orbit of Neptune in the Kuiper Belt, and a population that happened to get trapped in these Trojan swarms. When we do these calculations on a computer, and I'll show you an example of this in a second, what we find is the probability of getting captured is independent of where it formed. So these objects actually represent, if this whole picture is true, right, and it's just a theory, right, objects in the Trojan swarms represent objects that form throughout the outer solar system. So they're an excellent laboratory for seeing how things and conditions varied in this part of the solar system that all is basically empty except for Uranus and Neptune. So next slide. So I'm going to show you, this is a real numerical calculation I did of this event. Here's the sun, Jupiter, Saturn, and again, Neptune and Uranus with this disk. Next slide. Notice the time scale here. This system can be stable for long periods of time, right? Matter of fact, when you're standing up here and giving a talk, this seems like a long period of time. Right?
And what caused the instability to...
Don't blink, wait. Right? So it happened really quickly. It depends on the model. Okay, so the Nice model, we wrote the original Nice model papers in 2005, so it's been a long time. We're pushing 20 years, which is hard to believe. One thing that's hard to believe is when we came up with this idea, people thought we were absolutely nuts, right? Matter of fact, we thought we were absolutely nuts. And it still is the favored model for the evolution of the outer solar system, or versions of it, right, almost 20 years later. So it depends. There are several different ideas of what triggers the instability. Probably the simplest one to explain is that you can see that the gravitational... I can't see my... Can you see my pointer? Okay, then we'll do it this way. There are actually a few objects that are leaking out of the disk, right? And as a result, the planets are moving a little bit, right? And they hit a resonance with one another, where Jupiter is going around the sun twice for every time Saturn goes around exactly once, and that triggers the instability. Next slide. Thank you. So if all this is right, these objects, as I said, Trojans harbor objects that form throughout the outer solar system. It is a unique opportunity to study this population and how conditions varied in this disk as these objects formed, okay? But in order to understand what this population is telling us about the history of the solar system, we need to cover the diversity, right? And that's what Luci is designed to do. So next slide, please. And it does it with this totally amazing trajectory. I mean, this is really beautiful, and the guys that came up with this, who are in Lockheed Martin in South Denver, it was art to watch them do this, okay? It really is truly spectacular, and so I'm gonna show you it, okay? So what you have here is, here's the sun, here's the Earth, here's Jupiter, and here are the Luci targets that we're gonna go visit. So we launched, this says October 17th, but it actually was October 16th of 2021 on a rocket that looked very much like this. As I said, this was ULA in South Denver built this. We launched from Kennedy. And one of the things, in order to save money, believe it or not, Luci's $1 billion mission. And it's considered cheap from NASA's point of view, right? Excuse me. And so we're always in a fight to save money. One way we did that is by actually flying it on a very inexpensive, low-power rocket. As a result, when Luci moved away from the Earth, it moved away at a low velocity. So next slide. So you can see its orbit is very similar to the Earth's, or was, right? And then we're going to use a series of what we call Earth gravity assists, gravitational slingshots with the Earth, to change the orbit of the spacecraft, to pump it up so it can get out to Jupiter. The first one of these was last October, okay? Actually, people in Australia could see it. We got 300 kilometers above the surface of the Earth, and I'll show you, our solar rays are huge. So it was a naked eye object in Australia. And so we had that encounter then. Next slide. We ended up in an orbit now that's twice the orbital period of the Earth. During this loop, we're going to have an encounter in November of an asteroid that we call Dinkinesh, which is the Ethiopian name for the Luci fossil. It means you are wonderful, okay? It's a very small thing, so we're nicknaming it Dinky, but it's an object in the inner edge of the asteroid belt. And for our point of view, it's just a rehearsal. We're doing some innovative things on the spacecraft, and we want to make sure it all works before we actually get there. One thing, I'll talk about it a little bit in a minute. These are very fast encounters. If we blink, we lose it, and there's no going back, right? So we're trying to do everything we can to make sure that it's going to work when we get there. So that's our first encounter. We're going to come back in. Next slide.
What does MBA mean?
Main belt asteroid. We're going to have another Earth gravity assist in December of 2024. That's going to kick us out into the Trojans. Next slide. As we go out, we're going to pass an asteroid that we named Donald Johanson after the discovery of the Luci fossil. Okay. All these objects were originally unnamed, so we got a chance to name them. That's in April of 2025. Next slide. Then we're going to come out into the outer part of the solar system, enter the leading swarm, which we call the L4 swarm. And we're going to have 4 encounters. First with Everybody's and its satellite Cuppa, which we discovered with HST. I think I have slides in here about that, but Hubble Space Telescope. Next slide. 34 days later, this is going to be a busy, it's 15 months, right? It's going to be really busy. We're going to have an encounter with my second favorite object, Palomelli, and its satellite Sean. And I'll talk about its discovery because it's cool. Next slide. Then we go through Aphelion, the closest distance the spacecraft gets from the sun. Then the spacecraft's going to come back in. On the way back in, we encounter Eleufkis. Next slide. Orus. Next slide. Then we're going to use a trick that if you put an object that's its furthest distance from the sun is out near Jupiter, and its closest distance from the sun is near the Earth, its orbital period is half that of Jupiter's. As a result, on the first orbit, we go through the first leading swarm, and then on the next one, we go through the trailing swarm. Next slide. We're going to have another Earth gravity assist there to target our final object, which is this near equal mass binary called Patroclus Eminaceus. Okay? And you may say, well, wait a second, you're getting 4 here and 1 here? Why the asymmetry? And the answer is because this object has a really high inclination, but I was so interested in getting to see it that we used the last Earth gravity assist to sort of increase the height of the spacecraft, but that puts it in a region where the Trojans are low density, so we could only get 1. But it'll be worth it, no doubt. You know, I have to say, next slide. Oh, next slide. Okay, so here are our targets. And I have to say, you know, I was singing the praises of the people that designed this trajectory, and it truly is amazing. It's literally a work of art to find this. But it turns out it's also, we were very lucky. So one of the things when you propose to NASA for a mission, they ask you is, why now? Why can't we do this in a decade? Right? So as part of our analysis, we tried to find another trajectory, say if we launched in 2030, rather than 2021, right? How many things could we go see? And the answer was 3, and they weren't particularly interesting. So not only was this a work of art, but it was luck, right? Or I put it slightly a different way. I've spent my life doing dynamics, right? So I've been worshiping at the feet of the celestial mechanics gods, and they're paying me back with this. This is truly a rare and amazing thing. So remember I said diversity is the key, right? So I said we need to get all the spectral types, and we do. We've got 2 Cs, right? Keta and Nephrobetes. We've got 4 Ps, 1, 2, 3, 4, right? And 2 D-type asteroids. So we're really covering everything that we need to cover. But in addition to that, remember I'm telling you that we were lucky, right? Several of these are interesting objects to send the spacecraft to, even if it was the only place that the spacecraft was going. And so I'm going to talk about why some of these are special now. Next slide. So let's start off with Everybody's and Keta. Next slide. So Everybody's is the largest remnant of what we call the only disruptive collisional family in the Trojans. Every once in a while, 2 big asteroids will hit each other, and they will just go boom. Next slide. You can tell these because if you look at the orbits of the resulting objects, they all clump in space. So you can find these asteroids by looking for clumps in orbitals element spaces, right? We've never seen an object like this before, and so it's interesting to study because after all, if you think about it, the growth of planets is a dynamical problem, things are moving around the sun, and a collisional problem, things grow when they hit, and they stick when they grow. So understanding, well, I think we understand the dynamics pretty well. Kepler worked that, or Newton worked that out, right? And really, what goes into the models I've been showing you is just what Newton figured out. But the collisional process is much harder. Okay, as a result, going to study a collisional disruption event is going to be scientifically interesting. But what's more, when it comes to the trying to understand the diversity of these things, this object is really a mystery. Like I said, it's the only disruptive collisional family in the Trojan swarms. It's one. And it's a C. Remember I showed you those pie charts, right? And I said these were about roughly half Ds and half Ps with just a few Cs. It's about 7% of these gray guys are mixed in, and almost all of them are part of this family. So you go, what's the chance of one of the rarest objects in the Trojan swarms being involved in a rare collision in the Trojan swarm? And you start thinking, something's going on, right? And then when you look around asteroids, the main asteroid belt, there are lots of Ds and P main belt asteroids that are parts, but none of them are part of families. They all tend to be these gray objects. And you go, okay, something's going on. And I can think of two things that are going on. First, that these things are so fluffy and soft that they get hit and they go poof and are gone. I think that's unlikely. I think what's most likely is, remember I told you we don't know what makes these things red, right? And it could be that whatever makes them red is only skin deep, right? And then when you break them open, they're gray inside, right? That's what I think the answer is, and Luci will help us answer that, because when we get to the red objects, if the young craters on their surface should be gray, right, if their interiors are gray, right? Does that make sense? So that's exactly what we're trying to do with Luci. Okay, next slide. As I said, we discovered the satellite Cuppa with the Hubble Space Telescope. Here's some images. You see it sitting there? There? Yeah, right? And I must admit, this is where observers always amaze me. Because we got that image down, and I don't know if any of you have heard of Mike Brown. He's Planet 9, right, guy. Excuse me? And it deserved it. Okay? Which I think is what his book is called. Why? How I Killed Pluto? And, yeah. It's a funny story. But anyway, Mike and I are good friends. And he's on the Luci Science team, and he looked at this image and said, oh, there's a satellite. And I said, well, why is this a satellite and that not? Right? But, he's been doing this for years, and he recognized it. We got more time, and lo and behold, it's a satellite. Right? It's about 1 kilometer in diameter. We have now a good orbit. So we're going to be able to observe it when we fly by, because we're going to know where it is in the spacecraft side. So that's really cool. It's one of the smallest things in the outer solar system ever visited, right at this size, so it should be fun. Not only that, next slide, maybe it's not surprising that Everybody's, which was involved in this major collision, has this tiny satellite around it, because I've already showed you this movie before. Next slide. But if you look in the very center, what you find is fragments of the collision can end up in orbit around the body, right? So undoubtedly what Cuppa is a fragment of this collision. So not only we're going to be able to study the center thing that got hit and blew up basically, but we're going to see some of the fragments, right? And that's really cool. Next slide. Okay, next slide. Next slide. I want to talk about my favorite object, which is this binary. I keep saying that, although I'll show you. Paul Millie is pretty cool, but okay. We didn't know that when we put this together. Next slide. So, this binary consists of two objects that are almost exactly the same size. Okay, we know their shape because of stellar occultations, where star moves behind the object. I'm going to talk about that a little bit more, right? So they're about 100 kilometers in diameter. They're on a circular orbit around each other, separated about 700 kilometers, okay? This kind of object is extremely rare in the inner part of the solar system. And by inner part of the solar system, I mean inside the orbit of Neptune. Okay? But next slide. If you go out beyond Neptune in a region that we call the cold classical Kuiper belt, this is a region of the Kuiper belt that is beyond the orbit of planets, that are so far from the planets that they were not affected by planet formation. So they really consist of primordial objects. And when you look at that population, almost everything is a binary, including this. Remember Arrokoth, right? The New Horizons went past it a couple years ago, and it is a binary, right? So this is telling us, I think, pretty clearly that the first macroscopic things to form in the solar system tended to form as binaries, okay? If that's true, then Patroclus is one of these binaries that's within reach of our spacecraft because it's so close to the sun. It just happened to survive, because what really happened is during the planet formation process, that process was so violent that the binaries were just ripped apart by probably gravitational interactions with growing planets and each other and things like that. So you don't see them anymore. But Patroclus is just a rare survivor of that process. So we're really going to see really one of the more primordial objects that we can get to with the spacecraft. Next slide. Next slide, let's talk about Palomeli. Now I have to say, when we started this, I said, oh, Palomeli, it's small, it's not particularly interesting. And it turned out it too is incredibly interesting. So one thing you can do when you have a NASA mission is you can spend a lot of resources actually studying the objects before you get there. We're doing some innovative things with our targeting software to make sure that the objects stay within the field of view of our cameras, right? This is innovative software. It's never been flown before, right? One of the things we wanted to do was to make sure it's going to work, okay? The one we were most worried about was Palomeli because it was the smallest. So we've put an immense amount of time trying to study this from the ground. Next slide. And so we did this using stellar occultations, and I have some slides on that, so next slide. Stellar occultations, what we do, right, is as an asteroid is moving and there's a background star, the shadow of the asteroid will move across the Earth. If you put a bunch of telescopes along that path, you can measure what we call chords, right? You're looking at the star and you watch this. This is one of the observations we took. That star is about to be occulted by Palomeli. You see it disappears for a while, and then comes back. And given the fact that we know how far Palomeli is and how fast it's moving and how fast the Earth is moving, we can get a physical dimension of that particular chord, right? And if you put a lot of telescopes along perpendicular to the shadow, you can actually get the shapes of the asteroids. Does that make sense to everyone? Good, because I'm going to suggest if you're interested in doing this, it's done with a bunch of 16-inch telescopes. We have down near 66 and I-25, we have a warehouse that is stacked full of 150 of these things, which we deploy all around the world, okay, in order to observe these events. I think I've covered everything here. Next slide. So I'm just going to show you some of the occultation events we did at Palomeli. This was our first one. The biggest problem with observing these things is we don't really know where the object is very well, right? Because we don't have really, really good orbits on them. But these events tell us where it is. So slowly over time, as we observe more and more of them, we get better and better understanding of where the object is, and as a result, we can pack our telescopes closer and closer together, right? Because the error bars go down, and we can get better shapes. Does that make sense? Okay, so here's the first one we did in 2020, then we did one, this one was in Spain, I think, in 2021. Next slide. And you see they're getting better, right? Here is this is in March of 2022, and we got a great shape, for Palomelli, and we were surprised that about 20 seconds later, there was another dip in 2 telescopes. So we discovered a satellite, which we have nicknamed Sean. It's not named yet. The IAU will not let you name something unless you have a good orbit for it, which we don't. So the people who discovered it, they were in Australia. But the amateurs who discovered it decided they incorrectly interpreted the meaning of the word Palomelli, which they thought meant many sheep. Okay, so they named it after Sean the sheep. Okay, it turns out it means many, many songs. But okay, we're keeping Palomelli Sean until we can name it. Next slide, we've done 2 more, right here and here, and then this last one. This was a huge effort. We deployed 120 telescopes. Luckily, it was in Kansas, right? Because we wanted to make sure we got Sean again, and we did. I didn't show you it because it was just one dip, but you get the idea. So that was a huge effort. By the way, this is all run through here. People travel all over the world. We pay for travel. So if you're interested in getting involved in this, I think we're almost done. We may do 1 more or 2 more, right? But sign up, and if you're interested, you can join our team. Now I want you to go back through these again. Okay? No, go forward. Okay, well that doesn't tell you not much, but this one, it looks elongated, right? Okay, next slide. And it's definitely elongated, like football shape. Next slide. And it's always elongated. So what that's telling us, if you go back, next slide now, is this thing is almost shaped like a hamburger. It's incredibly flat, okay, around 3 to 1. There's the shape when you actually do the calculation, right? Now, people would have argued before this discovery of this shape that what you see in the Trojans are a collisionally evolved system. You made big things, and they've been grinding each other up and hitting one another, breaking apart and reaccreting. But there's no possible way that you can get this shape in that process. But the current ideas on how you form the first primordial objects will give you things at this shape. After all, Arakoth, that thing in the Kuiper Belt, is this shape. So I think we are very surprised, but I think this is a primordial object too. Okay, so we're going to be visiting 2 primordial objects in the Trojans, which, if you don't mind me saying, is really cool. Next slide. Now I forget what I do. Okay, so here's all our targets, right? The Trojans down here, and then we have Dinkinesh in November. And I must admit, I'm scared as hell because it's coming up really fast, and Donald Johansson. So let me talk about what we're going to do. Next slide. Oh, right, forgot about this. Remember I said diversity is a key, and I talked about the spectral types, but we have a lot of diversity. We have, large mass ratios of objects. These are both P's, so it's about 160 if you assume their densities are the same. Next slide. Right, we have different collisional histories, as I've already explained. Next slide. Okay, now what are we going to do? Well, to cover this kind of real estate, we have to be moving really fast, right? There's a lot of space between these objects, right? And so we're going to be flying by really quickly. We're not stopping and sniffing, right? We are just going by. Our encounter speeds go between 6 and 9 kilometers a second, okay? We cannot blink, all right? All the important science of each encounter is going to be about 2 hours. So over the entire mission, which is a 12-year mission, we get all our important science in about 24 hours, right? And the rest of the time is just basically flying between the objects. So what are we going to do? Basically, we're going to do everything that we can possibly do with remote sensing, okay? We're going to image to get geology. We're going to look at surface color power and composition. We're going to measure the Doppler shift of the spacecraft as we go by these things, measure how the gravity of the asteroid affects the trajectory of the spacecraft. From that, we're going to be able to get masses. And then with the imaging, we're going to get shapes. So we're going to be able to figure out the density, which is going to tell us something about the internal structure of the objects. Right? We're going to look for satellites and rings. Next slide. This is how we're doing this. This is my baby. Okay, let's put this in perspective. That is a 2-meter high gain antenna, so it's about like that, right? We're going further from the sun than any other solar powered spacecraft in history. So we have massive solar arrays, which are these two things here. They're 7.3 meters in diameter, and the spacecraft is roughly 50 feet from wingtip to wingtip. So it's big.
Interrupt and ask some of the LTO folks, how does that compare with the size of the radio dishes we have out there?
Outside, we have a 15-foot, so that's 4.5 meter, and a 16-foot, about the same size. And you're talking 21 feet across. Right. Whereas our dishes outside are 15. Right. It's massive, right? So, and they did something really cool with it, which I'm going to explain to you in a minute. I just love talking about our solar arrays, even though we've had some significant problems. On top of the spacecraft, so it's from here to here is about 14 feet. On top of the spacecraft is this platform where all our instruments are mounted and it's articulating, so we can move it. So this is what we call the instrument pointing platform. Here are our instruments. There are 4 or 5, depending on how you count it. There's basically an 8-inch telescope. So this is our high-resolution panchromatic camera. We have what we call the terminal tracking cameras. These were put on mainly so that we can make sure we're always pointing at our targets. These are panchromatic, but we're also going to get shapes of the objects with these cameras. We have a thermal infrared spectrograph, and we have what we call a Ralph, which is 2 instruments in one. It's a color camera plus a near-infrared imaging spectrograph. So here's our wavelength range from here. Down here, we go from about 4,000 angstroms out to 5 microns. So we're doing basically everything that we can do with remote sensing. Next slide. So this gives you an idea, putting in perspective of how big our solar arrays are. I've never seen one of these close up, so I don't really, doesn't help, but you get the idea. Next slide. Next slide. So here's a picture as we were putting the spacecraft together. This thing is so big. This was done, as I said, in Lockheed Martin down in South Denver. They did not have a clean room big enough that we could open up the spacecraft both sides, so we were only doing one at a time and kept having to flip the spacecraft over and rotate it around so we could get to the other solar array. All this is just support, right? These things are not made to be open in 1G, right? And the cool thing about this, besides the fact that it's so big, is it's made out of cloth. Next slide. Except for the arrays, just put a light underneath it. Everything that's gold here is cloth. Okay, and it opens and closes like an Oriental fan. Well, it'll never close again, but that's how it opened, right? Next slide. And the cool thing about it, here's the spacecraft on the shake table, right? Right. You want to make sure after you build this thing that it's not going to break when it launches. So you put it on a big shake table and the shakes know how to, luckily nothing fell out, which wasn't true in JWST when they first did it. Okay, but here are our solar arrays folded up, and it's all in there, folded up, it was 4 inches thick. Okay, isn't that cool? Yeah. Next slide. Here's our instrument, the instrument pointing platform with the instruments on it before it was put on the spacecraft. Again, here's Ralph, here's the thermal infrared spectrograph, here are our terminal tracking cameras and our 8-inch telescope. Next slide. And this gives you an idea what the field of view is of the instruments when we're flying both the Ralph, which has the infrared spectrographs, Lisa, and the color camera, MVIC. They're scanning instruments. They build up an image as they scan. So that's why I just show the width here and then show the arrows moving. But that gives you an idea of how big the field of views are. Next slide. Now I'm going to show you just some eye candy. This is the spacecraft down at Cape Kennedy before it was put into the fairing. A bunch of people, can you tell which one's me? Yeah, you can't get it. This is the spacecraft before it was put into the fairing. Next slide. This is one of my favorite pictures, taken at the same time. Somebody standing in one side of the fairing looking at the other. I think that's pretty cool. Next slide. This is the spacecraft on its way to the launch pad. This was all done at Cape Kennedy. Next slide. Okay, I'm going to need somebody. This is a video. We've gotten some well wishes. So just, do you want me to go back and do it? Just move the cursor around and you'll see. Now, just click on the arrow.
A little noisy, but I'm so excited. Lucy is going back in the sky of diamonds. Don't even love that. Anyway, if you meet anyone up there, Lucy, give them peace and love from me. And NASA, peace and love. It's just so great that we're heading out. I loved it when we reached Mars. Now we may be going a little bit further. It's a lot of room. Peace and love. Don't forget, my name is Ringo. Peace and love.
Like, you know, they cut the video and then he said, I didn't say who I was. So, like, anybody needed to, anyway.
That's all he says anymore.
It's peace and love. I know it. You know, probably too much drugs when he was doing this. So, by the way, he's coming to Denver. He'll be here on the June 6th giving a concert. And we've been invited backstage to meet him. So that's going to be super cool. Next slide. Oh, what? There you go. So here's pictures of the launch. Next slide. And like I said, you really have to look at these videos, right? Because we launched into a cloud deck, right? And then when the spacecraft erupted from the cloud deck, right, it looked like Close Encounters of the Third Kind with lights shining all over the place. It really is spectacular. I suggest you look at it. Actually, most people saw that. I was too close. To me, it just disappeared into the cloud deck and I never saw it again. But where the public was allowed to go, it was really a beautiful launch. Next slide. Okay, I'm going to show you some of the things we've done, just calibration and that kind of thing. This is one of my favorite. This was, if you remember, there was a lunar eclipse back in May, right? So at that time, here was Lucy and here was the Earth. So we observed it. You can see the Earth rotating here, right? And then you watch the moon disappears as it moves into the Earth's shadow. Isn't that cool? Oh, it'll repeat itself. There you go. So, I thought that was pretty cool. Next slide. This is during our EGA activities back in October 22. I like this picture too. Again, this is a picture of the Earth and the moon. And you know, you tend to think when you go outside that the moon is really bright, right? But you look at this, look how faint it is compared to the moon, to the Earth, right? It's only 7% albedo. Have you ever seen a moon rock? It's black. The moon is actually black, right? And this shows that. Next slide. During the EGA, we took some high-resolution images of the moon. The purpose of this was calibration. One of the things that Lucy really needs to be able to do well is observe craters on the Trojans. And so we wanted to see what is the smallest crater we can actually see. And so that's what this activity was designed for, but we've got some really beautiful images of the moon. Next slide. Oh, we've gotten some press. I thought this was pretty cool. The kids had no idea. It was really embarrassing. So, next slide. one thing that we did, NASA has this, call it a tradition, I guess, of putting plaques and things on their spacecraft. Remember, the Pioneer has the plaque, the Voyager has the record player. Those were all messages to aliens. But it turns out that Luci, right, is going to be put on an orbit at the end that is going to hang around for something like 2 million years. That's the average lifetime. So you can easily imagine 100 years from now, 1,000 years from now, 10,000 years from now, our descendants are astroarchaeologists. They're flying around the solar system, picking up our space junk, trying to figure out about our culture. So we decided to put a plaque on Luci, but rather than a message to the aliens, it's a message to our descendants. So we asked a bunch of notable cultural leaders. We reached out to US poet laureates. We reached out to people who won the Nobel Prize in literature. We have, Brian May of Queen is in here. He's an astronomer. I don't know if you knew that, right? And all the Beatles are in here, Carl Sagan. I mean, people have died. We just took quotes that we thought were relevant. But so that's on Luci. And up here, what I did was here are the orbits of the planets, right? And their the location at the time of launch, right? This is locked space, so it looks a little weird, right? But the basic idea, here's the orbit of Luci. So the basic idea is that sometime in the future, somebody finding this can look at the location of the planets and figure out when it was launched, okay, as a clock. Okay, next slide. This is where Luci is now. By the way, take a look at that website if you're interested. You can see, for example, here's Jupiter. The green is Earth, right? Mercury, Venus, Earth, Mars. We passed the orbit of Mars a couple months ago. Right, we're heading out to the inner part of the asteroid belt is here. This is Dinky, right? We're moving slower than Dinky is because we're closer to the sun. And as a result, it's going to catch up to us. And that'll happen in a few months. And I think that's it. Next slide. Oh, no. So let me put Luci in context. In the whole history of the robotic exploration of the main belt, we've observed 9 main belt asteroids. Right? And they've revolutionized our understanding of how the inner solar system formed. Right? Luci, one mission, and it's relatively low cost mission at that, is going to visit almost as many Trojans, 8. And we expect it to revolutionize our understanding of the formation of the outer solar system as much as these guys revolutionized our understanding of the inner solar system. Now I think I'm done. Yep. Thank you. Yeah, and what I didn't say, basically, right? And what I didn't say, right, is that, this geometry of going through the L4 and then the L5 is going to repeat basically forever. So, at the end of mission, if we still have resources left, fuel, and there's some other resources on the spacecraft, there'll probably be an extended mission and we'll probably go back and do more Trojans. Like I said, I'll be 74, I'm going to retire. So somebody else will have to worry about what we're going to do with it at the end.
It will repeat after how long?
This orbits about every 6 years.
Okay.
Right? So we're getting to the L4, right, in 2027, and then the L5 in 2033. So, and then that'll keep repeating.
Can you explain again the conditions that make those cluster zones where
it's just gravity.
Really?
Yeah. Like I said, the way to think this is actually not strictly true, but okay. But I say it anyway, right? The way to think about it, if you put something in front of a planet on a circular orbit around a star, okay, that's all you really need. That you can. Keep going, keep going. There are a lot of slides. Yeah, it's way back at the beginning.
Yeah, they continue all the way to the beginning.
No, go ahead. Go one more. Right here. Right, so if you put an object right there, the gravitational attraction of the sun, plus the gravitational attraction of Jupiter, plus the centrifugal force, basically all cancels out.
Gotcha. Okay.
Okay. Like I said, that's not quite true, but it's good enough.
Does Jupiter repulse?
No, it attracts,
Okay.
right?
But at the limit of what they can do by way of the other characteristics.
Yeah.
Okay.
I mean,
And that's why they.
I can, if you want to, I can try to explain it to you better, right? But you know, I'm not sure everybody else wants to know about resonant dynamics. So, but you know, if you want to come up, I can try to explain it to you some more. Yes.
Using this slide up on the right, we see two orange patches where the Trojans are.
Right.
You had an animation at one point, and all these little dots were moving.
Oh yeah.
Doing all kinds of stuff. And yet you're gonna get out there and expect them to be in the right spot?
Gravity is an amazing thing.
Okay.
Right? I mean, yeah. I mean, think about it. We're traveling, I think the whole mission is like 7 billion miles or something like that. And we're hitting a target in space that our error bars on our delivery is something like 20 kilometers. Now, that's not saying that we're doing that now.
20 kilometers compared to how close?
We're getting about 1,000 kilometers away from the targets. Yeah. Okay. Well, you know, as we approach, we take images. We use those images to figure out where we're going. Then we do little course corrections and walk our way in to get down to that 20 kilometers. But basically, we know exactly where we're going to be and when from now until the end.
That means you can see this thing as you approach it. You can see it from how far away?
We already have images of all our targets. So, and I should put that in this talk, actually, because that only happened a few months ago. One of the things we're worried about is what we call the phase function, which is how the brightness of the object changes as a function of viewing angle. Because one of the things that's very unusual about Luci is because of our geometry. Remember, we're approaching all our targets when the spacecraft is its furthest distance from the sun. And as a result, we're basically approaching from 90 degrees. Okay? So the spacecraft will be, the target here, the spacecraft here, and the sun's in the floor. Right? So, and one of the things, if you ever look at the moon, you can really see it, is that the brightness of the moon is a function of what we call the phase angle. And so if you look at it, particularly when it's near crescent, you know, the limb is brighter is significantly brighter, right, than the terminator, for example, right? And that's just because of the reflecting properties of the surfaces. So one of the things we're worried is that these things are going to get really faint when we get near 90 degrees. And remember, these are cameras, so we have to set exposure times to make sure we see it. So one of the things we need to know is how bright they're going to be when we're approaching at 90 degrees. So throughout the mission, we're going to be taking images of the object so we can figure out how bright it's going to be as a function of phase angle. Does that make sense? And so we already have our first observations of it.
Back to my original question, though. So we got these two orange patches of dots.
Yes.
And they're wiggling around.
Yeah, go to the next slide.
And we see some big.
Next slide. There you go.
That's the image I was.
Yeah.
Don't they interact? You've been observing them for a while. You know exactly what they're going to be.
They do not interact. There's not a lot of mass there.
Oh.
The only thing that you need to worry about is the gravitational effect of Jupiter.
So these are big dots, of course, compared to.
Oh yeah, if you were standing on a Trojan, you wouldn't.
They're just so tiny.
Yeah, they're 10 kilometers, and their separation is like the distance between the Earth and Mercury, on average. So if you were sitting on one of these things, right? This is why there's only one collisional family, right? They don't hit very often. There's a lot of space. If you were standing on one of them, you wouldn't know the rest of them were there with your naked eye, except occasionally something would come close, but it's very rare. Yes?
How hard is it to get through the main asteroid belt without hitting the main?
For the same argument, it's easy.
It's just that.
Yeah, we didn't even worry about thinking about it. Yeah. We were worried about micrometeorites, you know, little dust particles. So we have models that tell us how often the spacecraft is going to hit, right? Be hit, particularly as use solar rays, right? You can imagine a little dust grain hitting one of them or breaking them. So we calculated how much that's going to happen. And, you know, we put extra solar rays on it to make sure that it doesn't affect the power, right? All that we've done, but we never worried about actually hitting something the size of this building. It's just not going to happen. Now I said it. All right. It shouldn't happen.
These solar panels are like parasols that open up.
Yeah.
And there
Yeah.
was some excitement when they opened up in the beginning.
Yeah, one of them didn't open all the way. And
What's
it's
the status now?
it's not open all the way.
Okay, all right. Yeah,
But we're worried about it. But so like I said, they open like Oriental fans. So all open is 360 degrees, right? We're 355 plus or minus 2. So it's not a power issue, right? It's almost entirely open. The real concern is that these things are made out of cloth and they get their strength because of tension, okay? And the outer parts in particular of the array are not tensioned. So when we were particularly worried about our main engine burns, there are 4 of them. The first one is February of next year, okay? And we're worried that the spacecraft's gonna shake or something might flop up and hit. And I mean, there are things that can happen, but we've modeled it as best we can. We've worked really hard at trying to get it to latch, but we can't. And so we think we're okay.
So there is a latch at the end of the circle.
Yes, there's a latch at the end of the,
So what isn't quite?
right. So there's actually a lanyard, right, that's about that thick. It's a piece of tape made out of Kevlar, okay, so it's pretty strong, that's holding it all together. And it wasn't designed to do that.
There is a tension trying to open the last one, right?
Yeah, it's more complicated. It's actually the way the thing opens is by pulling on this lanyard, this tape, right? And the tape wrapped up on a spool, and because of the dynamics of the spacecraft during launch or the deployment, the tape fell off the spool and started wrapping up. Think of it like a fishing line. Started wrapping up and getting tangled around the motor spool. So, yeah.
It stuns me that.
The people who designed it promised me they fixed the design. And I said, I don't care. Yes, this won't happen again. I said, I don't care. So.
Also be aware that all of this final phase happened during the pandemic, and everybody still pulled together.
No, we were, if you go back and look at the reports NASA has on the effects of the pandemic on their missions, we were rated the least impacted of any mission.
And that's due to good leadership and a very dedicated team.
Yes, and timing.
Are
But
the charts available anywhere?
these charts,
The presentation?
if you just look online, you can find versions of this.
Okay.
And also, Hal graciously brought some of the mission.
Yes, there are stickers and stuff back there if you want.